Good evening. My name is William Malerich, and I'm an aerospace engineering student doing research in the Department of Aerospace Engineering and Mechanics under Dr. Chongze Hu. My research project is on molecular dynamics simulation and characterization of grain boundary segregation in the aluminum copper system. In this presentation, I'll first explain to you the theoretical background for my research, the software tools I use, how I use them, and then talk about the current state of my research and what I'll do in the future. So all metals are arranged into 3D repeating structures called formula units. And as a metal solidifies from a liquid, it does so by a process called nucleation, where small regions of the metal first reach the freezing point, and then those small regions solidify, and then the adjacent liquid atoms will attach to that small solidified region and assume its structure. And the result of that is that you end up with many microscopic, uniformly oriented regions within a metal called grains. And where these grains interface, we call that a grain boundary. So grains are characterized by their orientation. In the image here on the slide, those three numbers are what characterizes the orientation. And depending on the differences in orientation between adjacent grains, that can create inconsistencies in the properties of the grain boundary, such as changing the strain induced on their nearby atoms. And that can cause solute atoms in an alloy to preferentially move towards the grain boundary in a process called segregation. And that can dramatically impact material properties. So it's an area of important research in material science. The goal of this research is to build off of a previous paper by the Hu lab that established a methodology for determining the... So that means that LAMMPS uses Newtonian mechanics, not quantum mechanics, to simulate atoms, so it treats them as point masses with force fields around them. But those force fields are informed by the potential file, which is based off of... It's an embedded alloy method potential file, which means it's based off of density functional theory simulations, which do involve quantum. And are matched to real-life results. So it sort of simulates the quantum behavior. We run on the UA-HPC computing infrastructure, and all the analysis of the results of these simulations are done in the Open Visualization Tool, or OVITO. To generate these structures, we use the Hu Lab's Grain Boundary Project website, which contains a tool that allows me to put in certain geometric parameters and receive a structure that I can put into LAMMPS. And this is a simple process that only takes a few seconds to do. So for my methodology, once I create the structure, I first have to minimize it at 0 degrees Kelvin to ensure that the atoms are acting as they would in an actual simulation and don't contain any artifacts or strange behavior. So basically, we set them to 0 degrees Kelvin and allow the atoms to reach their lowest energy state. And then we equilibrate them at 100 Kelvin. And we do this because if we raise them to a higher temperature immediately, that would insert a lot of energy into the system quickly and disrupt the structure. So we do them at 100 before we raise them to a higher temperature. So you can see here in this image, within the yellow boxes, you can see that the area you can see through is changing, and that's because the atoms are slightly rearranging in the grain boundary area. So then what we do is we dope it by substituting a certain fraction of the atoms with the solute. So in this case, we're replacing some of the aluminum atoms with copper, which are seen here in blue. And then we can take that, and for this study, trying to replicate those exact results, we do it at room temperature or at any other temperature, simulate the segregation. And the way we do that is using Monte Carlo exchange. So the atoms are randomly swapped with their neighbors, and if that results in a decrease in the energy of the system, the swap is kept. But if it results in an increase in the energy of the system, the swap is undone. So for the preliminary results, so we were able to replicate the strength of the segregation observed in the experimental results, but there were structural inconsistencies between our model and the physical experiment. So in the images here, you can see that there is a defined bilayer segregation. In the bottom image, it's those two yellow atoms that were the most highly segregated region. But in our simulation, we saw more of a tri-layer segregation and a slightly differently arranged grain boundary interface. And we believe that this is, after modifying the boundary conditions for the simulation by changing their periodicity and increasing vacuum on one side, we think that the reason for this is that the embedded alloy method potential file does not properly account for the intermetallic compounds that can form at a high copper concentration and temperature near these grain boundaries. But the qualitative data we gathered about the bulk of the structure and the structure outside of that specific arrangement is still valid. So in terms of temperature dependence, we saw that there was a low segregation at lower temperature. And then as the temperature increased to 300 or 500 Kelvin, the segregation increased. And then above that point, it decreased as the alloy lost its structure. And we can actually quantify that by taking a common neighbor analysis, which shows the crystallographic arrangement of the atoms. So in here, the green are face-centered cubic structure, while the white is unorganized. So you can see in the 100 Kelvin and the 300 Kelvin, they're relatively similar. But in the 500 Kelvin, the disorganized area starts increasing. And we start seeing small inconsistencies in the bulk material. And we can also get some data on that through the centrosymmetry parameter, which shows us, essentially maps the symmetry of an atom's arrangement. So are the atoms around it symmetrical in all directions? So the blue is highly symmetrical, and red would be not symmetrical at all. So we can see again that it's relatively similar at 100 Kelvin and 300 Kelvin, and then increases pretty dramatically at 500, and also that the bulk material increases in entropy. And the result of this is that we have more atoms suspended in the bulk material that don't segregate out at a higher temperature of 500 Kelvin. And so for concentration dependence, we saw that as the concentration increased, the segregation strength decreased. And the likely reason for this is because as the copper atoms segregate to the grain boundary, they change those parameters in the stress fields that were actually forcing the segregation in the first place, which decreases the strength. So for future work, now that we know this embedded alloy method potential file does not quite work the way that the copper-silver one does, we're going to move to a different alloy system, but still use the same process for simulating the segregation and modeling the alloys. And we want to determine the impact of the segregation on material properties via crack propagation simulation, and then do qualitative analysis of the boundary with C++. That's all. Are there any questions?
Back on slide 8, I think you mentioned there's a tool by the Hu group for on their website to generate the structure. So I'm assuming there's like some parameters to define the morphology. Yes. So how many different structures would you generate? Are there many that you then look at for the segregation stuff, or I'm just curious how that works to feed into your experimentations? Yeah.
So for this research particularly, we were trying to examine just one or two specific grain boundaries, because we had seen in an experimental study from a different group some very particular segregation behavior that was interesting. And we thought if the embedded alloy potential file worked as the silver copper did, we would be able to find some interesting data about why it formed that. Unfortunately, it did not.
What type of analysis do you plan to perform on the simulation results using C++?
Yeah, so once we have results with C++, we'd like to do simulation to determine the free energy around the grain boundary, the amount of disorder, and the free volume, which is sort of how much open space is there, because those are very important parameters that determine segregation as well as the strength of the material.
How do your simulated results inform the mechanical testing and design of these alloys?
Yeah, so the eventual goal of all of this simulation is that the data will lead those who are building physical alloys to better understand the processes behind the strength of their materials and the segregation, and what concentrations and heat treatments are best for forming materials that meet their constraints.
Over what timescale are these simulations conducted, and how do you know it is long enough to recreate experimental results?
Yeah, so the time step for metals in lamps by default is 1 femtosecond, and we run these for on the order of 2 million femtoseconds, which is not a very long period of time, but they are not very large. They're only a couple hundred nanometers across, and we know that they're similar to experimental results because they achieve equilibrium at a certain point and stop changing.
You mentioned you used UAHPC resources. So can you describe something about the parallelism, the native parallelism of the simulation that allowed you to benefit from that? I mean,
Yeah.
what was it about you needed HPC resources for that?
Yeah, well, so first of all, it's just a lot of compute that is needed. It's like many millions and billions of processes that need to be done. And the parallelism in the UAHPC is very helpful. It allows us, so I, for instance, would run across 4 nodes and 16 tasks, which allows me to do it significantly faster than I would be able to on a single core. That reduces the time from days to hours.
So like why C++? Why not like NVIDIA's CUDA or some other kind of thing that's a parallel language?
I guess that those are the tools that have already been previously developed by the lab in C++. So I didn't want to have to remake all those tools for characterizing the grain boundary. All right, so this is our last presentation for today, so thank you for coming, and please join us again tomorrow at 11:30 a.m. when we'll resume.